Hello everyone and welcome to my channel. Today, I will be explaining two fundamental concepts in control engineering, transfer functions and state space. First, let's take a look at what a transfer function is. Consider a system G of S with an input U of S and output Y of S. The relationship is defined as Y of S divided by U of S equals G of S. The ratio of a single input to a single output is what we call the transfer function. Let's use a specific example to illustrate this. Here we have a slider with a mass m. It receives an input force, F of t. The damping coefficient is d, the stiffness is k, and the displacement is y of t. Then its equation of motion can be expressed as follows. F minus d times y dot minus k times y equals m times y double dot. Now, let's apply the Laplace transform to this equation. Let me give a brief introduction to the Laplace transform. Y dot transforms into s times y of s minus the y of 0. Y double dot transforms into s squared times y of s minus s times y of 0 minus y dot of 0, assuming the initial value y of 0 equals 0. These items can be deleted. Then the Laplace transform expressions for y dot and y double dot look like this. So, the equation above, after applying the Laplace transform, becomes the following. With this equation, we can isolate y of s and u of s. The ratio can be expressed as follows. This is the final form of the transfer function for this system. However, transfer function have several limitations. First, single input and single output. If you have multiple inputs and multiple outputs, you can't express the system at this kind of ratio. Second, the initial values must be 0, as we mentioned during the Laplace transform step earlier. Third, you can't understand the internal state changes. Transfer function only describes the external influence. To solve these problems, we need to use state space. Let's use the same example to explain state space. The slider has a mass m. It is subject to an external force, F. It has a damping coefficient d, stiffness k, and the displacement is y. Since state space operates in the time domain, we will simplify the notation and omit the of t. Let's rewrite the equation of motion. First, let's explain the standard form of the state space representation. X dot equals ax plus bu, y equals cx plus du. Here, x represents the state, y is the output, and u is the input. A, B, C, and D are matrices. Let's apply this to our example. Here, we assume we need two states, x1 equals y, which is the displacement, x2 equals y dot equals x1 dot, which is the velocity. Now, we are going to rewrite this equation into the state space form. Matrix x1 dot x2 dot equals A times x1 x2 plus B times u. U is input. Y equals C times x1 x2 plus du. First, x1 dot equals x2. This comes directly from our definition. Next, x2 dot is equal to y double dot. We need to derive the y double dot from the original differential equation. By dividing both sides of the equation by m, we obtain the following expression. Y double dot equals negative k over m times y minus d over m times y dot plus 1 over m times f. Now, let's substitute the variables. Here, y becomes x1, y dot becomes x2, and f becomes the input u. Combine these two equations, we can get the matrix A equals 0, 1 minus k over m minus d over m. And matrix B equals 0, 1 over m. This is the first equation for the state space. And we can rewrite the equation as below. x1 dot x2 dot equals O1 minus k over m minus d over m times x1, x2 plus O1 over m times u. Y equals, as you can see, this is the second equation of state space. It has two matrices, C and D. Y equals x1. This is what we defined. So here, D is 0. And C equals 1, 0. So the second equation we can write like this. 1, 0 times x1, x2. Okay. So we rewrite the equation to the state space form like this. In this way, we have successfully rewritten a differential equation into the state space form. Using these equations, we can solve the system as needed. In the next episode, we will explain how to actually apply transfer functions and state space. Thank you all for watching, and I'll see you in the next one.